All right, guys, welcome back. In this session, I want to circle back on some old documentation that I had previously, um, specifically OpenStack Cloud on premises or in the cloud, right? So in your test environment, you're actually building your on premises, your data center. So learning if you follow the other classes, I teach you how to do that, and some other videos if you have any questions on that. But what about OpenStack Cloud in the cloud? In the cloud, um, uh, we we design we when we talk about in the cloud, we talk about providers, and I'll get to you a little. I'll get some further down in this slide. We talk about minimum requirements for an OpenStack VM and how those minimum requirements work in your test environment versus how they would work in your test cloud environment or within your data center or in your production environment, right? So it's a little different than what you see from the vendors' websites, right? So the vendors will have their own information, and that's typically the information you see. But just remember, you're creating these minimum requirements based on what you have in mind or what your lab is built on or what your company um, wants to build for. So the absolute minimum specs depend on whether you're running either a control plane in your infrastructure services. And I give examples here in my PowerPoint presentation, like Keystone, Nova, Glance, right? And typically in a control plane infrastructure service, you know, you have two vCPUs, right? So when we're building these machines, Station Pro, right? And you have your typical RAM and you have your NIC card, you have your storage, et cetera, et cetera, et cetera, right? So when you're building these machines, you want to be able to know what you're building them for, right? And in this instance here, I built a machine, right? Based on memory, processor, disk, hard disk, CD, DVD adapter, et cetera, et cetera. This is just a blank machine, right? So when you're creating these machines, you're creating it based on what you want it to do. So in this lab or other labs, you create it on what you want, right? So what do you need it for? It all depends on what you're running, right? So it doesn't really matter what you're doing. Well, sorry, what you're running or you expect to run. You can eventually make changes to these environments as needed, right? Just remember, once you create them, yeah, they are deletable, right? You can delete them and recreate them as many times as you want. But in specific infrastructures, you have your vCPU, which is in a control plane. We need to create two vCPUs. Whereas you have an infrastructure service and you need a minimum of 4 to 8 GB of RAM and at least one network through two is recommended plus, but it is recommended for again separate management, tenant, and storage traffic. And I'll dive deep into that a little bit down into this presentation. And second is your end user service virtual machine. It's your tenant workload. Here. Okay, I'm gonna make this a little bit bigger. Show you how about this. We'll go make this a little bit better. And I will move this out of the way. See if I can make this a little bit bigger for you. All right, anyway, it doesn't matter. So, like I said, your tenant workload is your virtual machine. That's your end user server virtual machine. In my test environments, you're using the desktop Ubuntu desktop cloud, right? So when we're logging in, we have two different types of VMs for Ubuntu cloud, right? So our Ubuntu Canonical, Ubuntu desktop, and Ubuntu server, right? So So you have your desktop, which is more designed for personal computing. It has a graphical user interface or GAU, and it's obviously pre-installed productivity software. Again, while the server is more for an environment, you want to use that for just command line interface, light, right? Serverless. It's got greater resources. It's got greater resources. Give me 1 second. So you got greater resources, you have that efficiency, and the server. So both versions seem the same, share the same kernel and software repository, meaning that a GUI can be installed on a server or a server that can be installed on a desktop. They, but they differ in their own default package selections, right? So you have to understand the intended use, right, and et cetera, et cetera. But focus on why you're using a desktop versus a server, right? So in your environments, either a test, a lab, a demo, you've got your personal computers that are meant for daily tasks, web browsing, multimedia. This is important, right? Your user interface, your GUI is what features those graphics, right? So it makes that user-friendly experience. So it also comes with, again, the pre-installed software. I showed videos on this already and what its focus is about. So it's focus on that versus what the server, Ubuntu server is intended for. It's intended for hosting web files, and I'll show you a little bit more on the actual, not just the Ubuntu, but the virtual machines that we're going to be using and creating, and what we actually create these specific VMs for, because that's important, right? So you'll kind of see once we go um down into this presentation and how this works and whatnot, right? So you have your intended use for this server, and that's meant for host web file database, application services, managing networks, and powering enterprise deployments. Whereas a server by default, you know it features, in the desktop, it features the full graphical user interface, whereas in a server, you know it runs headless, right? So it's managed remotely. Usually it's managed with an SSH software, right? So for me, SSH software would be, um, I would use, for honestly, I would use Putty, right? Everybody's to each their own, right? But Putty is, like in some of my old videos, I've showed people how to use Putty, and I think I downloaded it. Yeah, and here it is. So here's the Putty configuration. you know the user interface, like I said, runs headless, managed remotely. Obviously we want to manage this remotely, but we don't want to manage this in a work group environment where everybody has access to it, um, you know and on your system, so that it runs often via the SSH, right? So you would connect via the host name, through SSH, and connect to the port in time, making sure that your computer is, um, on the same network, or VLAN, or virtual network. That way it's communicating with each other. And then you have and this is a great read. This makes sense. I just Googled conical desktops. This makes sense. It's proven. There's tons of books out there that you can read. You can definitely visit the Conical Ubuntu's website. But again, um, this will take your your information and kind of give you the right information, so that you're going to need this information, right? So I recommend understanding the fundamentals first, because the fundamentals make sense before you go out and experiment. That way you know what your fundamentals are, and you can go ahead and get your engineers to build it, right? Your engineers need to understand that. US system admins, as system engineers or cloud engineers, you guys need to understand how this works, right? Building your machine again on an Ubuntu server, there are its pre-installed applications, right? So you're going to have those pre-installed applications on the Ubuntu server. Like you're going to have oriented packages already included so that when you give yourself those commands, like open SSH server and lamp stack, and lamp obviously stands for Linux, as in lamp as in L, Linux, A as in Apache, M as in MySQL, and P as in PHP, and that's called your lamp stack. For all of these people that just learning, please hit the like and subscribe. You just learned that, or leave your comments in the chat. Love to hear them. Love, love the better, right? And again, in a desktop environment, you'll notice that the Ubuntu desktop comes with a wide array of general purpose software, like your web browser, right? So you have your Firefox, Mozilla. In a Microsoft environment, you have a Internet Explorer, well known as MS Edge, and default we're talking about, right? So you would have eventually want to download the browser on the Microsoft product. You would want to download the Microsoft Edge product on that, then that would be extra, right? So, and then you'll have your Libre Office suites. And I used to love Libre Office suites. We're talking about 20, 30 years ago. It's been around for a long time, right? So this and the different media players that they have within the desktop. Whereas again, you know, on a server, you'll have fires, you'll create your file servers, right? Or your um NFS file shares, right? So you'll have that. And when you focus on the actual desktop itself, differences between your desktop and your server, you have your usability productivity for a single user environment, whereas the server focus is on performance, optimization, scalability, and stability for workloads, right? So knowing the um, the requirements, right? The hardware requirements. So that's important. Um, know the difference. Very important, and I will send you guys a link on that in the chat, and I'll write that in the notes so you guys have that for the future, or just take a look at it, take a picture if you want to take a picture. You're more than welcome to. I'll leave it up here for the crowd in full time. I'll make this a little bit smaller, and you guys can go ahead and take a picture of that and stick it in your notes. So paper clippings or newspaper clippings. I used to do this all the time when I was a kid. I used to snap paper and newspaper clippings and book excerpts from different chapters and post those in my presentation. That definitely helped me discuss for discussion periods and stuff and different projects. So I definitely recommend you keep this for your information. So understand the difference between the desktop versus the server. Very, very important. And in this excerpt, it talks about intended use of it, your user interfaces, your pre-installed apps, and your focus, right? Um, then we start talking about different flavors within these different requirements. You have your tenant workload versus your control plane. You have in your tenant workload, in practice, you would use your two vCPUs. um, and you'd have your 2 to 4 GB RAM for realistic for useful workloads. It's more realistic for those useful your workloads. And in my example, as you guys can see, in one of my examples, I think I gave it here a while back. I just, for an example, it didn't matter. I don't remember what example it was, but this one I gave it one processor and 2 cores per processor, right? Follow my other videos if you want to learn about processors and hyperthreading and whatnot. Um, in practice, again, 2 vCPU for a tenant workload, and that's your end user server VM. If this is a control plane or an infrastructure service, you have your 2 CPUs, right? The more your VM, the more CPU, and I'll get to what it means to have more vCPUs or not. That's not really important, but it's just for the minimum requirements right now for our lab. In a production environment, we're gonna have tons of servers and different options and whatnot and flavors. And when we talk about the different flavors, we talk about how disks can be ephemeral, right? Or backed by Cinder volume. Cinder volume are part of block storage. Very important Cinder volumes, right? And your NIC cards can be split, like I said, two vCPUs, and a lot of my drawings that I draw here in my old videos, I always put two disks, two network cards for high availability. When you're working from your laptop or desktop, again, your laptop or desktop can be a Mac, can be a Windows 10 or 11 laptop that's connected to your router, and that'll connect to the internet, right? So within your laptop, you're going to be using the Workstation Pro, and there's videos on there and explain you how that works. I've also explained how the VMware vSphere and ESXi was explained as standalone member servers for work group. Um, I've also explained the memory contents to you and how the memory contents work, so which can be read back sorry, uh, sequentially. My apologies, by accessing specific memory addresses, right? So yeah, here's the drawing that I wanted to bring out here, which was important for your design. You're building it, right? But make sure you're building that with the operating system installed. You have your basic machine, or you bought your machine, or you bought your server, and you're now building this virtual machine for this environment, right? Because it's not just or in the cloud, right? So this can be in the cloud, or and you kind of get the gist of things when we talk about how I build on premises in your own environment, right? Using logical software versus in the cloud, also logically, where you have the different flavors that are pending there, right? So on our laptop, very simple. You know, you've got your laptop, your personally owned laptop. Don't use your work laptop. Please do not use your work laptop. I recommend do not use your work laptop. Go ahead and purchase one that's available out there on marketplaces. You know, there's some used ones out there, that have the amount of memory that you need. Just make sure you have enough memory to test it. Doesn't mean you need to buy yourself $100,000 laptop or $10,000 laptop or even $1,000 laptop, right? Just as long as it has the hardware resources and it's got the compatibility checks in place for your job and for your work or project, right? Just remember these Windows 10 laptops must be up to date. It's got to have the necessary drivers in there. Um, can't be outdated. It's got to be secure, right? So make sure that you're following up on those decisions when you're before you go ahead and design it, right? Um, think before you act. Talk about RAID here. Uh, talk about the different RAIDs. Uh, this one. Okay. Photon OS within it uses our ESXi, our vCenter uses our Photon OS, right? So when you're building those machines within the cluster, right, which is your ESXi, you're building these machines within the vSphere client. Um, it uses Photon OS, right, which is Linux based. There's some certified servers. Bare Metal uses different framework. I talked about this already. OpenStack again is your control plane, right? So we are definitely following along. If we're following along and not following along, and you weren't dozing off. Um, you know, we are on a control plane, right? So we're typically be using two CPUs, right? Your minimum, 48 GB of RAM and one NIC card, right? This is just a build these are just the minimum requirements for an OpenStack, right? There are different flavors, right? So typically, you know, NICs can be split for management, like I said, storage and tenant networks. And again, these flavors can be customized depending on the workload, right? And SLAs, right? So you have to have a best use case uh, as to why you're using these specific NIC cards and what you're using it for. And in this chart, I kind of put that in there, like you're tiny or small, you're medium, right? So if you have a one CPU, you have a tiny, it would be a tiny machine. So if you wanted to use the tiny flavor, you can use the one CPU to 1 to 2 GB of RAM, 10 GB disk, minimum one NIC card. And again, this is just for test VMs, low traffic web servers, right? If you're planning on building a lot of machines for testing and crashing purposes, right? You have your two and your four. There's a lot of and again, the small is meant for web servers. So like in your test or dev environments, you have a lot of software and developer engineers or architects that want to build these types of machines. Again, you can build these machines, uh, prepare these machines for your build, right? You have your small, right? Which is your two flavor, which is your two vCPU. You have your 2 to 4 RAM, which is your basic minimum, and minimum 20 disks just to install Ubuntu server, right? So these are again meant for web servers, small DBs, and test and dev environments, right? Then you get into the medium, the large, and the XL, where you have your 4 vCPU, your 4 to 8, right? Your 4 to 50 gig disks, and again, these can be ephemeral or just backed by block storage, right? Or backed by your Cinder volumes. And these are meant for like medium workloads, like you have a production web server or an app server, then that's where you want to, go ahead and design your your machine, right? So when you're going ahead and designing these, you're creating the new virtual machines based on the different flavors that it wants, right? So that's your on-premises environment. I'm not going to go through that whole thing. Just take a look at these mental notes, take a picture, and take a look at that later. Um, you know, you can go ahead and assign more vCPUs in an environment. It's not a big server. It doesn't necessarily mean that it needs a lot of vCPUs to run. It's first one running. But again, over the network, it can be heavy, and it does need power, right? And it does need there's a lot of IOPS and whatnot that go in and out, right? But why would you might assign, for example, let's say 4 vCPU, right? For example, you would, you know, assign a medium, for example. Um, in my example, again, we can go ahead and design that if we want. Again, it's up to you. But why would you um, might want to design a 4 vCPU machine versus a 2 vCPU machine? And these could be some questions that can be asked. And again, it's normal. It's normal to ask these questions. It's okay. People ask these questions all the time, right? And again, when you're building these, you're not going to install the operating system because you're building your bare metal machine in a logical environment, right? You know, you you have your two versus, let's say, 2 versus 4, right? In this environment, we can say that this is a 4 vCPU, but we can also say that there's a 2 vCPU, right? I'll kind of explain to you both as uh, just in case you want to learn, right? And this will make sense once I have this in place here. So, you have your workload demands and a lot of small production workloads, right? And that's typically you're not your demand, but I would say this could be like a concurrency, right? And these workload concurrencies are based on many small production workloads, right? So what that means is workloads like web servers, right? Databases, and those could be lightweight, right? And development or and development, right? Uh, Servers, right? Right? Or tests or development or test, right? You could say, right? These workloads need more than one vCPU. These workloads, and they need this or more than one vCPU core so that it handles multiple threads and requests efficiently, right? So these concurrent requests are important as the multiple threads are also important or secondly important, right? So understand that the concurrency is important, especially when you're assigning the two vCPU or even a four vCPU, right? As an example. So we'll talk about the difference between small and medium, um, which is important, right? And these are specific important instructions, right? And then when we talk about, let's say, we can also talk about and this is why I would want to assign it. You can also talk about processing, right? What do you mean? And that's in parallel. What do I mean by that? So even in a small application, um, often someone like you or I would perform multiple tasks, right? Or there'd be a lot of users performing multiple tasks, right? And this all happens, these tasks happen simultaneously. So serving these requests or HTTP requests or processing these jobs like your background jobs, handling logs, or even just your input and output, your IO or of managing your network, right? So that's what the processing in parallel is. Um, 2 vCPU allows these tasks to run in parallel, right? Um, this will avoid bottlenecking, like on just a single core, which will definitely slow down the entire VM. So make sure that you understand that this is important, right? Um, so 2 vCPUs allow tasks to run in parallel, right? Which will avoid um, bottlenecking from a single core or just, slowing down the entire VM, right? Virtual machine. Virtual machine. Apologize. Sometimes it's good to tell you what these mean. Central processing unit, so CPU. And I'm going to make note of that just in case for people that don't know what a CPU is. So CPU stands for central processing unit, right? Back in the late 90s, beginning millennial days, right? What a CPU is and what that is and whatnot. But again, CPU is and V stands for virtual, right? So when you see V, so you have your workload concurrency. We talk about processing, right? So allowing these vCPUs, um, as this discussion talks about, allowing our tasks to run in parallel, which will avoid bottlenecking from a single core or just slowing down the entire machine. And again, even small applications, like I said before, like your HTTP requests, processing background jobs, logging, managing network IOPS, or IO, sorry, input output. Um, that also gives us that practical balance between um, performance, cost, workload requirements, and how we can explain this or do this professionally, right? So there's a lot, there's a lot to learn, a lot of information, but kind of understand the actual fundamentals, because the fundamentals it helps a lot too, right? Knowing this, learning this more than once, doing this twice, over and over again, gets you to your goal, right? Again, why would you assign two vCPUs? Another reason would be for me would be overhead, right? And when we talk about overhead, I talk about the OS and application, right? And when we talk about OS and application, we talk about operating systems, right? Like your Linux and your Windows, consuming those, which would consume a cycle, a CPU cycle, for like your background processes, like your kernel tasks, your scheduling, your system services and memory management, right? It would also, again, the overhead between the OS and the application, would also allocate the reason why we would allocate two vCPUs, so that we ensure that the OS has enough headroom, which will prevent the OS from uh, performance, right? Throttling application performance, right? Which makes sense, right? So, we need that headroom and headroom, right? Is needed for BOS, right? So I think it's important when you're doing this kind of things, right? And understanding the overhead is important, just as much as the processing and the currency. But we also need to talk about cost and performance, right? Cost and performance, right? So we'd have to know the cost and performance. The cost and performance is important as well too, right? So let me get this here, get this out of the way. This should not be. Okay, so cost and performance. You have your cost here versus your performance, right? We need to offer a sweet spot for that entry level production workloads, right? So in this case, we offer two vCPUs. Um, but why? You know, Enough CPU resources would avoid from having performance issues down the road. And this is important. Like you'll see me do my labs, and when I do my labs, I always run into issues. It's just because I'm showing you something. I'm not uh, proofing it for all my labs, but I'm showing you how it's done, right? And even if it's easily, you can easily create it within your own laptops with the memory that you have in your laptops, then why not? Try it, test it, explain it, right? So I'm able to explain this to you guys because, showing you what I know what to do helps you in the long haul, right? So having that to avoid the performance issues, we need to have enough CPU resources, right? So that also includes that sweet spot for different production workloads, right? And not over provisioning, um, not over provisioning it, right? Making cloud costs low compared to a different medium, larger XL, right? Which costs more. So having plus four more, like 4, 8, 16, you'll have um, higher costs, obviously, than a two vCPU. So the cost difference is important. And I hear this all the time. Great solution, great architecture, purchasing it, uh, you're able to understand that, right? And it's especially important. This is important for development, right? So small scale deployments or just testing in general, like we're doing, right? We can use a two vCPU. I've done this many, 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 many times. And again, we're just doing this where a single vCPU uh, isn't sufficient for this, but we would a 4 vCPU would be unnecessary overhead, right? So it's unnecessary overhead, right? In this instance for business wise, but again, assigning it in a small OpenStack flavor map, right? We have our different, obviously, GCP where we would use an E2 small. We'd have a B2S on Azure, or we'd have a T3 dot small or medium on an AWS. Again, this practical balance, know your performance costs, right? And lastly, I want to talk about hypervisor scheduling. What do I mean? In any virtualized environment, like we're doing here, like in OpenStack or cloud providers, two vCPUs gives our hypervisor, right? We talk about this. I talk about this a million times. Um, Flexibility, right? So if I want to schedule these workloads efficiently across a physical cross physical cores, right? So give the hypervisor flexibility in order for us to schedule workloads efficiently across physical cores, right? So two vCPUs, right? I'm going to write this down. Remove the bold. So two vCPUs. And again, I want you to watch this video twice. I want you to understand it because, you know, it's the same everywhere. But like I said, it's how you apply your actions, right? You know, everybody's great at what they do, right? You always want to you don't want to fine tune everybody's work, but you also want to be able to fine tune your own work, right? That way you get the confidence and you build trust, right? And uh, you build that knowledge in your head, right? So, you know, in V2, in hypervising schedule, when we do assignment to vCPU, you know, and this is important, right? Especially when you're assigning these two vCPU. You want to be able to give flexibility, right? Right. So we'll say two vCPU gives the hypervisor flexibility, right, to schedule workloads efficiently across physical cores. It also helps prevent degradation of performance, right? So this can be due to your CPU contention, and that could be from other VMs on the same host. So if it's on the same host, there's other VMs on the same host that can also uh, prevent performance, especially when you're scheduling um, these hypervisors in virtualized environments, right? Especially like within our OpenStack and our cloud providers, right? So understand that assigning these two vCPUs to a small VM ensures that it can handle light production workloads for testing, right? But again, it also supports that parallel processing, like I told you, and that execution and OS overhead and overhead for OS and application, right? So, and again, lastly, we have your cost and performance. So it's important to understand um, that as well too, right? Uh, if you don't, again, if you don't have enough space and you're thinking in your head, but what about a 1V CPU? I don't recommend it, right? Um, in a tiny flavor, right? This is why they call it a 1V CPU. Again, there's its reasoning for like, but don't need that parallel processing like we just talked about, or just any light workloads like, you know, you're testing a blank virtual machine and you're moving it from an active to a passive server, right? Or an active to an active server, right? And this is good for like, you know, moving files over, you know, test or dev VMs, you know, you're testing that, or you're even just your minimal web servers or even microservices. And this is where I would use that for those microservices, right? Or low traffic applications. And again, the reasoning you're going to think about, again, you're talking about the burstability, you're talking about the cost efficiency, you're talking about the requirements, the minimal requirements, and you're also talking about the contention for resources, right? So understand that reasoning, and it's not suitable for workloads that require that parallel processing, like I said, right? But it's important, and again, which will avoid the bottlenecking, right? But um or just even multi-threaded apps or moderate concurrencies, right? So know your different types of flavors, know them, know the differences, understand the advantages, understand its limitations. Give yourself its professional takeaways, right? Tiny obviously is minimal cost, suitable for threaded work, single threaded workloads, whereas your small is just more of a small scale production with that parallel processing that we spoke about. um, with the parallel processing, and it has the OS overhead for OS, sorry, for OS and application, and affordable, right? Um, Remember, the bigger you go, the more demand is involved, the more optimization you're looking at, the more environment simulation you want, and the more virtualization overhead scheduling, right? So, for example, in this OpenStack, it uses the KVM or QUEMU, which is another video that I explained to you guys on that. I talked about that in other videos. If you guys are following me, which use that's hypervisor CPU scheduling, right? So having 4 CPUs gives the hypervisor flexibility, right? So when we want to map workloads efficiently, or even just to improve responsiveness, right? So for a balanced OpenStack VM flavor, my recommendation is again vCPUs 2 to 4 depending on the workload. In summary, your RAM 4 minimum, 8 if you're running heavy apps or services. Nick, 1 at least if you're looking to try 2 for high availability. Yeah, in our test environment you want 2 or more. If you want to separate the traffic and you're showing people how to separate the traffic for that, right? And right, and again, when we talk about traffic, we also talk about the minimum, right? And best practice. So we look at our network cards and how VNICs, virtual network interface cards, so VNIC, and I'm also going to write that down for you. Uh, VNIC is a virtual network interface card, right? So that's important to note, right? So the minimum 1 NIC management plus team, and that's what your 1 NIC card's going to do. It's going to manage your manage plus your tenant traffic together, right? Whereas your 2 NICs, separation of management and doing this over and over again, many years, you want to separate your management for control plane and your data plane tenant traffic. So having 2 is also highly available, redundant, right? And also highly and eloquently important, right? So in production, often 3+ NICs, why? And I'll explain to you why. Even 4 NICs are good. And the reason why is you have your one for your network management control, your tenant traffic, right? Your heartbeat. Your management control could be your heartbeat or a heartbeat NIC to see if it's packets are going in and out, controlling your network, and storage, right? So you have your Cinder, your Swift, your Ceph, right? Storage is important, and having a separate network card is important, right? Dedicated. And again, you also have your external, your public access, but that's optional, right? That's only for access outside, right? So it'll have its dedicated network card, right? So you'll build your machine, you build a machine here, for example, right? And you're adding your NIC cards. And I use triangles, right angle triangles. So I have my right angle triangles, 1, 2, and I'll be right back. So You'll have your 4 network cards, again, optional, like I said, right? You have your 3. In production, often you will see 3 for best practice, but 2 is meant for control plane management and data plane, right? So you'll have your 2 different planes. But in production, you'll see 3 or even 4, right? As a fourth as an optional, right? So you'll have that optional choice to decide what you want, right? Um, and they'll all be managing separate and deciding differently, right? Another thing I want to talk about is mapping to your cloud providers. And that's the whole point here for OpenStack in the cloud is mapping. How are we going to map this to the cloud? We have our on-premises environment. Let's say we just want to map it to the cloud using our 3 providers. And these are the big 3. I call this the triad. You have your GCP, your Microsoft Azure, which is your IaaS, and Google Cloud Platform, right? And then you also have your Amazon Web Services, your AWS, right? Uh, you want to when we talk about these 3 and mapping to these, there I think about 4 key principles behind the mapping part of it and to the cloud providers. And you know, these 4 are your vCPU, which is your virtual um, central processing unit count, and the virtual central processing unit matches or slightly exceeds your OpenStack flavor to accommodate a hypervisor schedule, like we talked about in earlier slides, and burstable workloads, right? We also talk about, and if you want to know what a burstable workload is, it's typically defined as running low to moderate baseline CPU utilization, right? So burstable workload, they don't require and they don't require high CPU performance, but needs that short burst of additional CPU resources to handle any spikes in demand, right? So you always have your spikes, uh, your your spikes, right? Your CPU throttling across time, right? So you'll have your CPU strikes, right? And this is what I mean, like your ups and downs, right? On an axis, right? And this is very important as well too. It's a little smaller here, just to kind of give you guys a longer time, right? Over a long period of time, over a short period of time, right? So you have those um spikes on demand, right? And those spikes on demand, those workloads are common in both the cloud and virtualized environments, right? So when we talk about a workload running low to moderate baselines for CPU utilization, then that workload temporarily demands more CPU, right? Where it can burst above the baseline, right? So if we have a baseline utilization of 50%, and I'm going to do a different color to go at half mass here, right? That'll be our 50% mark, for example, 50% utilization, right? Um, you It'll demand the CPU, it'll demand, obviously it'll demand more, but it can burst above the baseline, so it'll consume unused capacity on the physical host, right? And another example of burstable workloads, which is also highly important, is when the cloud providers implement using CPU credits or just shared hypervisor schedules. So, for example, I think AWS uses T series for that. So they do that. They'll implement that. These different cloud providers. So, for example, AWS, if I'm not mistaken, uses T series. That's through AWS. And then Azure uses B series, and GCP, which is also one of my favorites, uses the E2 series, right? Uh, I'm not going to Google that, but you can go ahead and Google that and read up on the series. So understand that. Again, it has its characteristics, burstable workloads, right? It's got its performance baseline, it's got its peaks, it's got its time limit, it's got its cost effectiveness. How ideal are these workloads that don't need 100% CPU all the time, right? How cost effective is that? When you're developing and testing a VM, you have your developers occasionally compile code, right, and run tasks. So how important is that? And I used to deal with that a lot, right? And most of the time, the VMs, they're idle and or just lightly used, right? Whereas your low traffic web server handle occasional spikes, and again, like I stated before, they handle those low traffic web servers. They handle occasional spikes, right? And I told you what spikes are because we designed it already. Short ones too. I'll do a little short one over time. Right? Right? And then we'll give it a big spike up. Right. So they handle occasional spikes when in HTTP requests, right? So normal operation will use minimum whereas a normal operation, this low traffic web server uses minimal CPU, and the peaks require short bursts, right? So you'll see a short burst on the peak, right? On the peak itself. Let me see if I can, like this one here is a short peak, right? Um, then there's background jobs running in the background, like your processes, right? So an example, task manager. To give you a better example, you have your task manager, what processes are running in the background, right? And understanding how that works. Um, these background jobs or processes or tasks like cron jobs or log parsing or even just patch processing. Um, burst This will also be as sort of an example of that. And these background jobs typically idle because but occasionally demand higher spikes. So you'll have to understand the examples of workloads, right, in background jobs, and that's how a background job works. And when you look at the different background jobs, again, they're typically idle, but occasionally demand the CPU spikes. And then you have your microservices and your small containers, right? And this is one of my next videos that I want to come to, right? Where in a microservice or a small container, you handle small intermittent workloads, right? In a microservice, whereas your small containers, you have many containers that may run even concurrently without high CPU usage most of the time, right? So to understand good to understand what I'm saying because it makes sense, right? Uh, if you have to rewind back and forth to understand that, just do that because I'm not going to repeat the self again. Why do we use burstable VMs? And when you hear the word burstable, again, we talk about elasticity, right? Cost efficiency and predictable performance of spikes, right? So, you have your cost efficiency, you pay a smaller baseline VM you pay for that, where you're not really a fully provisioned one, right? So you'll pay for a smaller baseline VM and not a fully provisioned one. So these are why burstable VMs are important, right? Um, so when you're creating them with the non-consistent CPUs, right? You'll need in case of some short bursts, and you'll have to measure that on your VMs to see whether or not it's important to raise the CPU performance, right? So elasticity, VM handles spikes without over provisioning resources all the time, and this is why we use burstable VMs. So understand what that meaning is for the burstable workload. I think I've explained this a bunch of times. And I will give you guys a chart here of here. Give me 1 second while I input this into your, see if you guys can get that off of second here. See if I can get this for you. I just got to look for it. Okay, there you go. So, and this, I'm going to select this and give this to you guys as a good read and a good review. You guys can take that and put that in your notes. For vCPU, and when we talk about the key principles behind mapping to that, we talk about the vCPU, and again, this is still vCPU count, right? We talked about central processing unit, virtual central processing unit, right? Uh, if we go back to this thing now, we should have our chart here. So this is where, you know, these are some sort of cloud examples for cloud providers, since we're talking about cloud providers. And I will take that. Oh, I'll take this and I'm going to post it in my next slide for you guys to review. So when we talk about different providers, let's see this charted. Okay, so different VM types and series for different cloud providers, right? So you have for example, just to make this a little bit easier, and kind of go back to where we were talking about, right? When we talk about, again, its character, we talk about its characteristics, we talked about the definition, we talked about examples of different types of workloads. We also talked about why using burst loads VMs. We also talk about our next topic is to talk about cloud examples, right? You have your three cloud providers, you have your AWS, your GCP, and your Azure. You have your different types and series, right? So in an AWS environment, you have a T3 and T4G environment. And these are the different types. And then you'll have your series of types in tandem, right? So you have your VM type is a T3 and a series would be a T4G, right? How does bursting work, right? In this instance, so in AWS, it uses CPU credits. And I mentioned that word before about CPU credits, and again, it idles periods, right? Accrues credits, which are spent during those bursts, and again, bursts are peaks, right? Uh, GCP environment, you have your VM E2 series, right? This is, sorry, VM type series. There's no series on top of that. It's just a VM type. So then you have your E2 series, right? Your VM and then your series type. And it'll have different subcategories of that when you go online. And I might have a link to show you later, but I'll show you what I mean by that. You'll see it, right? And these VMs, again, how does bursting work on that specific provider, right? The VM can exceed baselines, right? CPUs temporarily using shared physical cores, right? Your physical cores. So it can exceed the baseline temporarily using the shared physical cores that's shared within our cloud provider, right? So within their data center, with inside the availability zone, uh, right, or availability set. Um, and sorry, and then you'll also have your Azure, right? And within Azure, you have your CPU credits and a B series, right? That's where, you know, The CPU credits in the B series accumulates when idle and allows these short bursts above the baseline. So whatever our baseline is, right? So in this instance, it's 50%, right? Anything above our baseline. So what happens is in the B series, it'll accumulate when idle. So if it's idle, right? Idle, which is idle is 50%, uh, and allow short bursts above the baseline. So anything short. So you'll see this little peak here. Let me see if I can draw this. So this little peak, that's what that means, right? So that's important to understand. So they're ideal for lightweight or tasks, right? That need occasional high CPU, but they mostly run on low usage, right? So anything below that 50%. So which is good. I recommend 75% as a minimum, but again, it's best not to have anything below 65 to 75%. Especially when you're assigning burstable instances like tinies or smalls. That'll avoid over provisioning while um, the tiny or small while maintaining performance where it matters, right? So there's different baselines, conceptual initiatives that really make this conception and intuitive. Sorry. Um, so understand that. Watch this twice. I'd love to post a picture for you guys, but I'll have to find one right now. Um, and I'll let you guys know in a little bit. Okay. So I'm going to go back to out of my drawing board and then I'll move this out of the way. Put this in the corner here so that we can space for our big timer here. So understand that. So we're saying the utilization baseline is 50 for now in this instance, but I recommend 65 to 75, right? Um, different environments and architectures, they have different ways of utilizing CPU spaces and whatnot. This is separate from where I'm going with this. There's different architectures that I've seen and different uh, things that I've run into, right, with in terms of the diagrams and whatnot. And you know when you have two servers with an operating system and an application server, building a second server when the utilization reaches, that's something that I've seen before. Like you can split them into tiers, right? So you'll have a server, for example, with a web server on an operating system. You'll have the web server, application, and database all in one, right? So if I were to draw that out, and if we were to split it into tiers, right? This is a different, but we're talking about it's the same concept, but you have your server, right? And then your server, you'll have your different, you have your operating system, right? And then you have your app, your web server application and database that sit on top of that, your services, right? So we can split those into different sections, right? So for example, if this is the OS level here, you have your web server, right? And then you'll have your, oops, say for example, you'll have your application, right? Which is a little bit lower. Let me see if I can go back here. Apologize. So you'll have throughput, like let's say, for example, you'll have three servers like this in a small, big environment. You'll have this server, which is just a little bit smaller, right? Which is below just midpoint, right? And then this will be 3/4 of the way down, and then you'll have your database, right? Which is your lowest point. Um, so this will be your web server, your WS, right? And then you have your app, right? And then you have your database, your DB, right? And this is your OS, right? So you'll have your OS, and then this is what splitting them into tiers is. So you're splitting them into tiers, and this is what 3 tiers would look like in this instance, right? You have your web server tier, your application tier, and your database tier, right? And that's important too, right? And this is where you can kind of, um, you know, build in an application where you can build different virtual machines within those load balancers. But in this instance, you have your utilization, right? So this is midpoint utilization here. So this will be your utilization, right? Graph. And so if this was a 50% utilization, utilization, understandable, right? So you have your 50%. If this was overutilized, the web server, and there was a lot of HTTP requests and traffic coming in, right? Oh, not pen, right? It was coming in, getting a lot of in traffic, in traffic, in traffic, and this would be at a standstill. What you would do is create another version of this, right? You would create that. Obviously, you'd create that other version of it, right, in another server. Right? These virtual machines can also be created in an auto-scaling group. Obviously, that sits within your public subnets or, internal subnets, NAT gateways, which have your NACLs. Again, it's a different architecture. It's, different for applications, right? And different for the different tiers that are involved. Um, So there are other tiers. Just give me 1 second. I want to give you some more examples of what tiers are, different options, right? And within these dependencies and applications, you have your library content as well too. Uh, you know, right? You'll have your you'll have your dependencies and applications. You'll have the library content between two servers, right? Between your app and your web server, right? So these two servers, right? And then they can be conflicting with each other as well within the one server, right? So it's best sometimes to have two servers. Um, you'll have a different version of an application which has a new library that conflicts with the library, right? There's a library here, right? And the new version, so the OS, let's say for example 1.0 is now 2.0 version of this application has a new library, right? So it'd be L2, right? And L 1.0, right? And that new library conflicts with the library that's in here. So if this was library 1.0, right? Conflicts, there's a big confliction there, right? And it creates a big problem, right? So understand that. There's also different logics that we can walk through and talk through. Hopefully, I could talk through in different environments or different meetings or different videos that you're going to see from me in terms of 3-tier architectures and monolithic application logic, and then your 3-tier architecture, adding redundancy, different things like adding redundancy to a web server, for example, right? um, After adding it, like how would that work? Adding different multiple servers with an operating system, separate operating system in each, and how after adding the redundancy to a web server or adding a second server to the web server alleviates the issue, right? So then we can add redundancy to the application and database here. right? So we can play along, right, in multiple ways, different ways of tooling, right? So stick along as we will do that in future topics, right? So I'm going to go ahead and save this picture as an example. I hope you guys understand this. Please ask questions if you don't. So, right, we also talk about RAM. RAM, obviously, second, we have it ensures enough memory for typical applications without over provisioning. Third, we have our workloads suitability. So, for example, an E2 for a lightweight burstable workload, an N2 version, right, for a production grade, and that'll give us consistent performance. We also talked about performance balance many times and how that works, you know, and it avoids the unnecessary costs while we could still provide sufficient resources for flavors equivalency that are intended for our OpenStack environments, right? We also talk about RAM. RAM obviously ensures that our VM has enough memory, which is random access memory, right? So RAM is random access memory. For anybody asking. And again, that's for both our operating system and our application workloads, as we saw in this picture here. Um, avoid performance degradation, different architectures. We could show different ways of doing it, and which way works for you, especially when you're going ahead and do that, right? So, and that'll be these performance degradations are usually happen from swapping or just memory pressure, right? We talked about memory contents and all that stuff before under their class. So hopefully you guys remember that. So cloud providers often standardize RAM, random access memory, in increments. So we can select slightly more RAM than the minimum recommended, which is optimal on an open stack, right? Which will allow for headroom. And we talked about headroom, as headroom is important, right? When we talk about assignments, right? And we talked about that overhead for OS and application, right? And that's needed for the OS. Um, and this is more for caching, again, OS buffers, background processes, particularly for production. So this is a work in progress, right? For many companies, kind of review and reevaluate that, especially in big environments, that are running these heavy load applications, right? So being able to design these, with the intention in mind, try it first, try in a test environment, see if that works, add, you know, pressure, give yourself a lot of information, run a lot of scripts, get your team to help you run these scripts and, try these different scenarios. That way you're able to know whether or not this is the perfect plan for you, right? Um, it's tough to know right away. You won't eventually get it the first time, but it takes a little bit of time to understand um, how much you're going to need and how much you're not going to need, right? Don't overcommit yourself either, right? So, if the medium flavor recommends 48, don't overcommit it. It's not worth it. Choosing 16 and GCP, for example, you have an N2 standard 4, N2 standard 4, N2 dash standard 4. And I'll explain that too to you guys. And this one here, when you choose that 4, it gives you that 16 GB, right? In GCP. So if we go to, I think I have a link here. Let me double check. Different links here. I think I have something here. To somewhere. Link, link, link. Do I have a link? Ah, here it is. So this is the machine type here. So here's an example I want to show you. Right? And Let's open up the new web page, and I will log into the GCP. And this is where, you have your, it's called the type family, right? You have your compute engine machine resources for Google Cloud platforms, right? So in this series, it's got different families on this page, and you can go down the different machine versions on the right-hand side once you log in, and it'll give you your different machine series versions. And this one here has flexible sizes between 2 to 128, right? So, and this will have up to zero, half, not recommended half because it won't work. It'll just be like a machine with no memory that doesn't even turn on, right? But you can't install anything on that, right? It's really awkward for me to actually see that there. I guess different reasons for that, but again, it's also offered, right? And you have your name, your CPU name here, which is isolate, and these are offered in specific regions and zones. And you can go ahead and check those different regions and zones, right? Your central US and your east US regions. So make sure you understand the nomenclature, right? And what that means, right? And what these lists and what these names are, right? So if you are a GCP person, understand that, the naming convention too, especially when you're describing it or you're talking about it to people. So in this N2 series that we're going to be using as an example for this purpose, it'll be a general purpose machine. That's where the N2 series comes in. And you have your storage, your compute, your memory, accelerator, core mark, platforms, GPUs, et cetera, et cetera. Different flavors are there, right? Different opportunity, right? Different naming conventions, different limitations, different disk types supported for these series VMs, right? So understand that there's a ton of literature here for you to look at, right? And this will give you the different types. So in our example, we used 2.4 and 2 standard dash 4, which is our 4 vCPU. And this is what we're going to build in the cloud, right? So we're going to actually you would actually build one in the cloud here, right? So you would log into your cloud provider, sign in, or console, right? And then log in. I'm not going to log in now, but you would go ahead and do that. Share your results, that'll be your homework assignment, is create an N2 compute engine machine, right? Which is a general purpose. I want you to create one. Let me know. So this will give you all the information that you're looking for, right? And I'll give you the different reasons as to why you need these different machines and what the workloads are for these different uh, general purpose type machines, right? So in this instance, the N series is meant for web traffic, containerized microservices, business intelligence apps, desktops, CRM apps, batch processing, storage and archive. And that's if you're going to GCP. Azure and AWS, Amazon Web Services, and Microsoft Azure have their own machine nomenclature, and I've got videos on that explaining how that works. Take a look at this, and then you have your ML training and interference for AI. You have your low traffic, and you have your tau, T do T, right? Which is your tau T2A and tau T2D, right? And these are different scale out workloads, burstable workloads that scale out, web servers, again, containerized microservices. But in our instance, we're going to be using our N2, and this is all based on, performance, right? And the different families that are out there, right? Different lakehead families. I think I explained that. But take a look at this release note for more information. Let's go back to this one here. So, yeah, so these are the different types of machines. So in our instance, we're going to be using this T2, which is up to 16 GB of RAM, right, for 4 vCPU, and then you have your 8 GB. These are all standard, right? Pre-defined. These are just implemented on single hardware threads or or logical core, or just one of the available CPU platforms, right? So maximum, again, maximum egress can exceed the numbers up to 10 given. So the actual egress bandwidth depends on the IP or destination IP and some other factors. Right? You can read up on this stuff, right? But know the different name. So you'll hear this a lot. And this link will help you determine and reference and guide to what you need to know, right? Um, then we talk about workloads suitability, right? So the different VM families, like I showed you, GCP, you have your E2, your N2, or B series in Azure. These are optimized for different workload patterns, right? And these are designed for burstable workloads, right? So that's important. We need to, right? So if you're looking for a burstable workload, you can use your E2 or B series Azure VMs, right? And if it's just for high performance database server, app server, or mid to large workload, you use your N2 server family compute. And if you're selecting a family aligned with workload, ensure that the CPU consistency, memory performance, and network throughput are appropriate to the application's needs. Okay. Our last principle behind mapping to cloud providers is professional grading of this. You have to incur costs per vCPU, central processing unit, and random access memory and attached storage. So over provisioning increases your costs without performance gain that's proportional, right? Without proportional performance gain, while under provisioning risks performance bottlenecks, right? So keep that in mind. When we talk about mapping, it balances adequate resources to meet workload requirements while we could still avoid uh, unnecessary over allocation or just achieving the cost effective yet performance solution, right? So in my example, right, you choose an E2 small over an N2 small for a lightweight web server, it'll reduce cost while you can still support expected traffic, right? So this is meant for that reason. For your production environment, production medium workloads or in production medium workloads, N2 standard 4 ensures performance and reliability without overpaying for extra vCPU or RAM, right? So you can try that and talk about that. Different mappings for compute, storage, network, and consideration. I'm going to leave this for another video. I'm going to stop for today and I'm going to say thank you. If you have any questions or comments, please feel free to message me in the comments below, and I will talk to you about a part 2 in our next video. Again, thank you. Have a great Friday and all the best.